Finding the maxima or minima of a function. These are also called local extreme values of a function. There are two techniques. One of them is first derivative test and another is second derivative test. So let's discuss the first derivative test. This test says that at a point x equals to c, if the derivative of function changes its sign from positive to negative, it means that the function was first increasing up to point C and then starts decreasing. So obviously the point x equals to C is point of local maxima. But if the reverse of it is true, at x equals to C, if the derivative changes sign from negative to positive, in that case the function was first decreasing like that and then starts increasing at point x equals to C. So obviously x equals to C is point of local minima. In case of no change of sign, there must be some behavior. If there is no change of sign, then such a point is called inflection point. At inflection point, the function was either still increasing, but still it changes some direction of the function, or it was still decreasing and there was a change in the direction of the function, but the function keeps increasing or decreasing respectively here as well. Now let's discuss the second derivative test. According to this test, x equals to C is any point in the domain of the function. X equals to C is point of local maxima if derivative of the function at C is 0 and its second derivative at this point C is less than 0. While x equals to C is point of local minima if the first derivative at C is 0 but the second derivative at C is positive. In case if the second derivative of the function is 0 at that point, x equals to C is inflection point. At the point of inflection, the shape of the function is usually S shaped, something like this. This particular point is the inflection point. Sometimes the function has this kind of shape, and these two are inflection point. Now let's have some examples to check these two theorems. For example, the function is x over 1 minus x square, and we have to apply the first derivative test only. We have to find the extreme value using first derivative test. The derivative of this function is, the denominator will be 1 minus x square whole square, while the numerator will be 1 into 1 minus x square minus x into minus 2x. So it is 1 minus x square plus 2x square over 1 minus x squares whole square. So we see the answers become 1 plus x square divided by 1 minus x square whole square. Clearly the domain of the function is the set of real numbers except for positive and negative 1. And we can see that because the denominator 1 minus x square is always positive and the numerator is also positive because 1 plus x square is always greater than 0, while 1 minus x squares whole square is greater than 0 for all values of x belonging to the domain, the set of real numbers except for minus 1 and 1. So hence the first derivative is strictly increasing function. So this function attains a point of maximum at any point inside this domain. This function has no well-defined maxima, by the way, but at x equals to 0, the value of the function is simply 0 over 1 equals to 0, which is the least value of this function. Because it is strictly increasing function, fx is strictly increasing function, it can be observed because the first derivative of the function is always positive. So fx is strictly increasing function, and a strictly increasing function doesn't have any well-defined maxima, but yes, it should have, or it's likely to have a minima, and the minimum value here is 0. So x equals to 0 is point of minima. Let's have another example. Suppose the function is 3x square minus 18x plus 2. Let's find its first derivative. The first derivative is 6x minus 18, and it can further be factorized as 6 times x minus 3. It can clearly be observed that below x equals to 3, the derivative of the function is negative, while the derivative of the function is positive on the right of x equals to 3. So at x equals to 3, f dash x changing sign, changing its sign from negative to positive, it means that the point x equals to 3 is point of local maxima, because the function was first decreasing and then it starts increasing, so it must have touched the point of local, I'm sorry, it is point of local minima. It is because the function was first decreasing and then starts increasing, so it must be the point of local minima. Let's have another example. Suppose the function is 3x raised to 4 plus 4x cubed minus 12x square plus 12. Let's find its first derivative, which is 12x cubed plus 12x square minus 24x. We can take 12x common out of it. It becomes x square plus x minus 2. It can be factorized to further as x plus 2 times x minus 1. So here the application of first and second derivative test both are quite easy. So we have to test the behavior of the function at three critical points, which are respectively minus 2, 0 and 1. The critical points are obtained by when we equate the first derivative of the function equals to 0. So the point where the first derivative is 0, that point is called critical point. So equating 12x into x plus 2, x minus 1 equals to 0, we get x equals to minus 2, 0 and 1. Now instead of applying first derivative test, let's discuss the second derivative test, because testing it according to first derivative test looks a little complicated. So finding the second derivative of the function at that point, I get 36x square plus 24x minus 24. Let's find the value of the second derivative at each of the critical points. The value of the second derivative at 0 is minus 24, which is negative. So x equals to 0 is local maxima. Now that's its value, second derivative's value at 1, we get 36 plus 24 minus 24, which is 36. So x equals to 1 is, that is greater than 0. So it is point of local minima. Now if we find the value of the second derivative at 2, it will be 36 at negative 2. We need to find it at negative 2. So 36 into 4 plus 24 into minus 2 minus 24. It is 144 minus 48 minus 24, which is 72, again greater than 0. So x equals to minus 2 is also local minima.